Wait, have you guys got it?
Nothing on the test.
Yes, I'll go.
It's application questions.
We got into the what disease is caused by this
Yeah.
bacteria. Yeah.
We didn't talk about it.
And it's like, I mean, it was fun coming out and because they showed a picture. It's like, I've never seen this picture. It's like weird. This is old. This.
Hello, morning. There's a homework. It's due anytime between Wednesday and midterm, I guess. Officially on D2L due. For Friday is also okay. Midterm will cover everything that we covered until today, I suppose, right? Until the end of the lecture today. That's what midterm will. I haven't decided yet what to do on Wednesday. I might do like last time. I might do a review, or I might start the new chapter. I haven't decided yet. Any questions or any comments concerning the midterm or anything? We have talked about how a magnetic field can exert a force on a moving charge. And we want to extend that idea a little. I should change this. So we talked about a magnetic force. On a moving charge. Here, magnetic force means we represent it by the letter B. This is very much like an electric field. That's what a magnet that you stick onto a refrigerator creates. And in the presence of a magnetic field, if you have a moving charge will be represented by Q, and a moving charge will be having a velocity, so it's Q times V. So that's the idea. What's the effect on a moving charge if you bring it close to a magnet? And we said that the force is given by Q times V as a vector. And we said there is a vector product. So this is a cross which has a special meaning associated with it. This is an operation between two vectors. So that's the first vector is the velocity. Second vector is the magnetic field. The order of these vectors matter. So it is given by the vector product of these two quantities. We interpreted it in terms of magnitude and direction. So magnitude of this force would be Q times V, where magnitude of the charge comes in magnitude of the velocity. It doesn't matter whether it's positive or negative. And the magnitude of the magnetic field, whenever I do not write a vector sign on top, it means that it's a magnitude of that quantity. And that is the sign of the angle comes into picture, like where angle theta is angle between you have two vectors. It can be put on a plane, and it's an angle between the velocity v and the magnetic field B. There's a direction also associated with it. It's a vector, so you need to find the direction. If it is being done algebraically, it will automatically give you the direction if you know how to do QV cross B as a vector product. But we have been thinking in terms of magnitude and direction because it is more intuitive, and that's given in terms of what we said, right hand rule. And the right hand rule involves, so if you have the fingers are in the direction of the first vector, in this case the velocity, palm faces the second vector, which is the magnetic field, and the thumb is in the direction of the force. Even though we have, in the context we are talking about, this is given as V, B, and F, the velocity, magnetic field, and the force. This is more generic. This is a mathematical operation. You can think of this as the first vector, second vector, and that's the resultant vector. So the resultant vector is always perpendicular to the plane that contains the first and the second vector. So that's another way of looking at it. We have a moving charge. That's what is the basic player, or what is feeling the force here. We also know that if you have a current carrying wire in electrical circuits, when we were talking about a battery connected to a resistor and a capacitor, we said charges move around in a wire, and we define what is called a current. So current is basically a moving charge, so or a set of moving charge. So you expect that this force should get affected on the current carrying wire. So let's talk about a current versus moving charge, right? What's the connection between them? So moving charge and a current carrying a current in a wire. Well, I remember, let me. We have Q times V. Let's write this as Q times length over time. So let's say that is a length. So since it's a vector, let me write that as a vector L over time. So there's some velocity. So this is a charge is moving. So how much distance does it move in a certain direction? This is the distance it moves in a certain direction divided by how much time does it take. That's the idea of velocity, and that's what it is. Now earlier the time was with respect to the distance or the displacement. Let me move it with respect to Q, and you see that this is Q over T times L. And then you can interpret, remember your definition of current was charge, how much charge goes through a certain point in a certain amount of time. So you can change this definition immediately and write it in terms of the current. So this is current times the length L. So the moving charge that we have been talking about has this another interpretation in the context of current carrying wires, that it is a current in the wire multiplied by the length. Now, what does that mean? Length of what? So we have a wire going from point A to point B. This could be the battery, and this is connected to a component there. That's a current I. And current I does not have any direction, but the length L here has a direction, or I should repeat, current has a sense of direction in the sense it could be going towards or in the opposite direction of the wire. But the wire itself could be in whatever direction you want to. So the direction has an association with the length itself because it is geometric. You can actually move it around. But the sense, whether it is, for example, this is a wire, right? You don't really associate a direction associated with it. So the geometry of the length is given by the wire itself, but the direction is given by the direction of the current. It matters whether it is going to the right or to the left. So in this case, I is the current that is going through the wire, and L is the length of this wire, and the direction is given by the direction of the current. So even though when we say length L, it is the length of the wire, but the direction is given from the current. So L here is length of the wires. Let's say magnitude is length of wire. Direction of L is given by the direction of the current. Direction of I. And I could be either in width, like if you think of a line or a road, it could be either going along this way or that way. That's only two possibilities. So again, L has a direction associated with it, which is given by the direction of the current, and L itself, the magnitude of the length is the length of the wire itself. Once we have this idea, once we have replaced, or we say that whenever there is a current carrying wire, it is basically a set of moving charges. Q times V can be thought of as current times length. Then we can talk about, instead of talking about current, a magnetic force on a moving charge, we can talk about a magnetic force on a current carrying wire, right? Because the idea is Q times V gets replaced by I times L. So let's do that. So magnetic force on a current carrying wire, on a current, let's say. By current, I mean current carrying wire. So that's an idea. The force now is given by, you just replace, same idea, everything remains the same, except that you now talk in terms of IL cross P. Right, how much is the current in the wire times the length L and times B. Again, magnitude and direction. So it's magnitude is F is this time I times L. Everything is magnitude. The sign does not come in. ILB times sine of the angle between now the L and B. So angle theta is angle between L and B. And the direction is given by right hand rule, except that this time right hand rule remains the same. It is the first vector times the second vector. Remember earlier the first vector was the velocity in that case. This time the first vector is the length L. So your fingers this time point in the direction of the current. So fingers in the direction of current, or L, which has the direction of current in it. Palm along B, or palm faces B. Faces B. And we have thumb in the direction of the force. Once we have this correspondence, then we can immediately go and start working on wires. Instead of talking about charges, we can talk about a set of wires and talk about what is the magnetic force on that. So as an example, a very similar example shows up in your homework, or probably identical, is example. Let's say there is a magnetic field, this time in the plane of the board. Typically, I try to point it inside into the board. This is the magnetic field going to the right. And immediately you can change this problem by saying that the magnetic field is going into the board. That's another possibility, an immediate possibility. You should try to attempt on that. And let's say there is a loop of a wire. So say that's a current carrying wire. And that could be current going, let's say, counterclockwise. So that's I here. If it goes in here, it has to go to the other direction there and comes in this way. Let's give some lengths here. Let's not say this is equal lengths. Let's say this is A and that's B. So that's the length of this wire. That's the length of that wire. Once I give you A and B, it is clear that if this is right triangle, then this will be C will be A square plus B square. So let's say this is C, or C is clearly A square plus B square. And this is given to be the magnetic field. Let's put in some numbers so that we can work on them. Let's say B is 0.05. 0.26 digits are Tesla. A, let's say, is about 15 centimeters. B, let's say, is about 25 centimeters. And so A, B, what else do we need? And the current, how much is the current passing through this? Let's say that's about 3.0. Let's say amps. It's a large current, 3 amps. Usually milliamps is the amount of current that typically goes through wires, especially in electronic components. 3 amps will be in a wire that is connected to the fridge or a microwave. Those are the instruments or appliances that take up a lot of current. With this, let's say what is the magnetic force? Let's begin with the bottom one, so side B, let's say. Just to get a label to that side, that's the side B. And what's the magnetic force on side B? Let's say this is magnetic force on side B. That's a label which says that that's the force on side B. That's equal to the current that is going through. Current will be the same in all, so it's the same I times the length of side B. Let's say this is L of side B. That's the length of side B. That's a notation there, and crossed with the magnetic field, which in this case is to the right. So that's your equation. And let's try to evaluate this. Magnitude will be you should try to figure out what that, before I write down in the next half a minute or so, you should try to decipher what will be that force. It should be very, if if you understand the cross product, then you should be able to immediately tell what that magnitude is, even without putting in the number. So let's calculate that. So f of b is equal to the magnitudes, which is I, no direction involved, the length, which is b, right? So instead of writing L of b, or maybe I can keep writing a length of side b, which is b times the magnetic field times the sine of the angle between the current and the magnetic field. The current is in this direction, is going towards the horizontal and going to the right when I'm facing the board. And the magnetic field is also going in that same direction, which means that the angle is zero. Right? Angle between this wire and the magnetic field is zero. And if that angle is zero, sine of zero is zero. So immediately, no calculation needed, but zero. So that's what I was trying to say, that you should try to decide from life. Just by looking at the diagram, you could have said, oh, that particular piece of wire from this point to this point is not going to experience any magnetic force, since the wire is in the same direction as the magnetic field. And unlike electric charges experiencing a force from electric field, when you're in the same direction, when you're moving in the same direction as the magnetic field, then the magnetic field does not sense you, and so it doesn't exert any force on you. So that's the magnetic force. Direction, it doesn't make any sense to talk about direction when that's zero, right? So you don't have to talk about any direction. If something is zero, then it doesn't have any direction. So that's side B. So let's talk about side A. So let's say, what's the force on side A? This is force on side A now is equal to current times the length of the side A times the magnetic field. Again, the magnitude is F of A is I times LA times B times sine of the angle. Now again, this time this side A is going down and the magnetic field is horizontal. The length of the side is vertical. The angle between them is 90 degrees. So that's 90 degrees. And if sine of the 90 is equal to 1, so basically the sine contribution is exactly equal to 1. And what exactly is this force? That's equal to the current, which is 3 amps, times the length A, which is 0.15 in meters, and the magnetic field is 0.05. And let me try to fit that in there. So 15 into 5, 75 into 3, that's 225. And there are 4, right? 225. So this is 225 into the 10 raised to minus 2 here, 10 raised to minus 2, that's 10 raised to minus 4. And the force is in newtons. You can say this is 22.5 millinewtons if you want. Or since I should work in 3 sig digits because I gave the numbers between 2 sig digits. So this is 23 millinewtons. What's the direction of this force? That's direction now. So we have to use our right hand rule, point the fingers in the direction of the current that's coming in. So it will be like this. It is usually, I cannot move the board. You people can actually move the sheet of paper. It often helps to move the paper itself instead of actually doing gymnastics with your hand, for example. So point it down, and the palm has to point in the direction of the magnetic field. So that will be this, and you open your thumb and you will notice that the thumb is coming out of the board. So fingers down in the direction of A, right? Magnetic field pointing to my, when I'm facing you, to my left, and then open the thumb comes out of the board, and that's how you get it. And make sure you use your right hand rule. You're writing with your right hand. It's convenient, very easy to realize or use the left hand. So it's coming out of the board. So it is out of the board. Or in your case, out of page. Any questions on that? I think it should be reasonably clear. Current, length, and a magnetic field, and there is a right hand rule that says that it comes out of the force. So what it means is that this particular wire experiences a force, so this is going to be pulled out. Like if let go, if this piece was on its own, this will try to come out of the board. And we will now see that this wire actually experiences a force into the board, so they try to rotate around. So it's not that they will actually move in this direction. This is going to experience the force into the board. This will experience the force out of the board. So they tend to rotate instead of actually moving in that direction. But that we have not seen yet. As of now, what the only thing we can say is that this part of the wire experiences a force coming out of the board. This wire does not experience any force when the magnetic field is going to the left. Typically, what I do is that I change this direction of the magnetic field. Various things I can do. I can change the geometry. I can move this triangle in any direction I want to. I can move the magnetic field in any direction I want to. I can make it go down. I can make it go left, and so on. And I can also make the magnetic field go into the board or coming out of the board. So those are the ways I can change this problem. And typically, I do ask a problem on magnetic current. So there are a lot of possibilities in there. So make sure you try to understand what are the details going in this example. Okay, so that's two sides done. Now we have side C remaining. So let's do side C. And side C, as you can expect, might be a little more work because it is not aligned or perpendicular to it. So there is an angle theta coming in, but we'll see that it actually is not that bad. So side B, side C, actually, sorry. And yeah, this is still in the board. Side C would be, there's a force FC. That's I times the length LC crossed with the magnetic field. Magnitude will be F of C, or the force on the side C is the magnitude of the current I times the length C. So that's the length of side C. That's A squared plus B squared. Here we can calculate that even though we're not given a C specifically. Times B times the angle between them. Angle between LC and B. We are not given that clearly, so let's see what that is. So this is the direction of the magnetic field. L is going that way, so that's that angle. Well, let's say this is beta. Or actually, maybe better if I say this is angle beta. And this will be 180 minus beta. In either way, it should be okay. So that's 180 minus beta. And then you will realize that sine of an angle which is subtracted from 180 is exactly the same as the sine of angle itself. You can see that from the following diagram. The sine function looks like this. That's 0, that's 180, and that's 360. And somewhere here is 90 exactly in between. And you notice that if you were slightly away from angle 0 and slightly less than angle 0, these two are the same numbers. If you were having an x-axis, the value of the function a little on the right side of 0 and a little on the less side from 180, that's exactly the same. That's a way of remembering if you want to draw the diagram. Otherwise, you can memorize, often you just memorize this, that sine of 180 minus angle beta is the angle beta itself. So this is the same as sine of beta, but it's not 0 or 1, right? Sine of beta there. So let's see what that is. So that's equal to I times B. Let me write this to the first, and LC times sine of beta. So you have a right triangle. Let me draw that again here. So you have a right triangle which has a length LC. That's angle beta. And if you ask what is the sine of the angle beta, that's nothing but the opposite over the hypotenuse. Right? Sine of the angle beta is opposite over the hypotenuse. So that means that the hypotenuse times the sine of beta, this whole thing is actually the opposite side. Right? That will be your side A. So this is the same as I times B times LA. Is that clear? Because again, maybe I should say this is length LA. LA over LC is sine of beta, which means that LA is equal to LC times sine of beta. So the angle there was exactly coming in such a way that it was only the projection of the length in perpendicular to the direction of the magnetic field that contributes. And that's a generic thing that happens, that whenever you have a length, it is a projection of this length perpendicular to the magnetic field that contributes. Anything that is parallel to the magnetic field does not contribute because that force is 0. So break this line into tiny vertical and horizontal pieces. All the vertical pieces contribute, all the horizontal pieces go to 0. So overall, it is just the side A. So the projection of the length on perpendicular to the magnetic field is what contributes. And that's just this. So that's what is that magnitude? Let's put in the numbers. That should be exactly the same as this, right? Because this was 1. It is I LA times B. I don't have to do the calculation. I've once done that. So that will be 23 millinewtons, or just for clarity, let me say what that is. So 3 times magnetic field is 0.05, and the length A is 0.15. That's 23 millinewtons. Yes, please.
I think you got the 0.05 and 0.15 mixed up.
Here I wrote it slightly differently, right? You're right. You're trying to compare this with this, right?
Yeah.
But here I had written length earlier.
Oh,
It's okay. The multiplication is going to give the same number. But here my point was that magnetic field is 0.05 and length is 0.15. So it's better to write it like this. Both are correct. No problem. But thanks for pointing out. But the force it experiences, at least the magnitude of the force it experiences, exactly the same as earlier. What about direction? If the direction also comes out to be the same, that means it will be 2 times the force, but we will see that it's not going to be in the same direction. It will be in the opposite direction. So let's see how we calculate the direction. Now we have, this is the direction, right? That's your current. So I point my fingers in the direction of the current, and a magnetic field has to be facing the or the palm has to be facing the magnetic field. So I pointed it in this direction, and then I can rotate it. So I rotate it in such a way that the palm is facing the magnetic field, and then open the hub, and it is going into the board, right? So that's into the board. That's into the board. So we have all three forces now. Let's now do F total. F total on this whole loop. Right now we are talking about a loop here. So we are asking what is the total force on this loop? What does it try to do? Does it try to come out of the board? Does it try to go into the board? Does it move to the left? Does it move to the right? So anything could happen when it's experiencing a force. But we are seeing that FA plus FB plus FC, if we take care of the directions and the magnitude, FB is exactly 0. And these two are acting in the opposite direction. So this is exactly equal to 0. So this is not going to move. Right? So this is, as far as the force goes, this whole wire is not, the center of the wire is not going to move at all because the total force is 0. In some places of the wire is experiencing a force inward. In certain places it's moving outward. So it is going to have a motion. That's what we're going to talk next. But in general, the force is 0. So let's, it seems like this is a coincidence that for a right triangle, this is happening, but that's not the case. This is in general to any closed loop of wire will have a total force 0. So let me state that as a theorem if you want. So magnetic force on a current carrying loop of wire. By loop, I mean it has to come back, it has to finish the circle. That's what I mean by a loop, current carrying loop in a uniform magnetic field. By uniform, I mean it should be the same everywhere on the loop. It cannot change from on one side. It is possible that, especially if you put a refrigerator magnet here, it will be stronger closer to the magnet. So this is having a larger magnetic field. That part is having a weaker magnetic field. That's not what we are saying. It has to be uniform, like gravity, for example, 9.8 is everywhere the same when we are close to the surface of Earth. So it is a uniform magnetic field that's necessary. Is 0. And always that's true. And you can actually use that to your, use that as a trick. We already saw that it was a little more work to calculate the force on the hypotenuse. So if you knew that the force was 0, you already calculate the force on A, force on B. You know that the total force is going to be 0. So the force on C will be exactly opposite to that of the force on A. So that's one way of concluding that, and that's perfectly fine. You don't have to evaluate it all the time. If you know this result, then you can use that. If there is no magnetic force, does a loop not experience anything? No, that's not completely correct. It does experience a torque. So let's define what is called a magnetic dipole moment. We had defined a similar concept called an electric dipole moment, which is basically a positive and a negative charge separated by a certain distance. A magnetic dipole moment is for a loop of wire. So you are talking about a loop of wire, loop of current carrying wire. You associate an area to the loop. So area of the loop, so let's say area A. It is a vector, as the area you associate to the loop is a vector. Magnitude is the area itself. Magnitude of the area is area itself. The area of, let's say, of a circle is pi r squared. What about the direction? Direction of the area is the direction perpendicular to the plane containing the loop. For example, if I have a loop of circular wire like this, and there is a current I going through this, the plane is this. And now I have to associate a direction to that. One is that if I say there is a plane in there, and now if you have a plane, the direction perpendicular to that could be inward into the board or out of the board. There are two directions associated with the plane, one going in and one going out. So now to get the direction, so here is a second right-hand rule if you want. The second right-hand rule, it is basically the same right-hand rule, but it's good to remember it as second right-hand rule, it might help. So if you allow me, this is right-hand rule. So this is second right-hand rule. And now what is the second right-hand rule? I have to give you the rule again. In this case, you don't use three directions, there is only two. One is the curl of the fingers. Now use your fingers to curl it in the direction of the current, right? So this is a curl, and while you're curling it, look for the thumb. The thumb is coming out of the board. If I were curling it in the other direction, the thumb will be going into the board. So the second right-hand rule is the curl of fingers is in the direction of the current, I, and the thumb in that position, I have to associate here, I will be talking about the magnetic moment. So this is the magnetic moment, M. And here it is I, so you can also say this is area, right? Curl of the, it is a curl of the fingers, it's in the direction of current. Actually, here we are talking about area, right? So I was talking about direction of area, sorry. So this is the direction of A. So that's A. So that's the direction of A. Okay, so we have area and that is a current going through the wire, and we define the magnetic moment, so magnetic dipole moment, M, will be defined as the current itself in the wire times the area A, but now it has a vector associated with it. I times A, where its direction is coming from the direction of the area, and the magnitude is coming from I times the area. So that's the two, the product of these two quantities. That's the magnetic dipole moment. So we said that there is a loop of wire. It does not experience any net force. Each piece of the wire can experience a force, but the total force is zero. But now we said it has a magnetic moment, but we still want to say what happens to this loop of wire. Does it not do anything? It actually does one thing, and that is that it orients itself. It doesn't actually move, but it orients itself, it rotates itself. So let's talk about that. So loop of wire does not experience any force, but it experiences a torque. Torque on a magnetic dipole moment. So let's see what is the torque on the dipole moment. Let's say this is your magnetic field. And let's say this loop that we are talking about, this is a circular loop. It could be having a square shape or a rectangular shape, doesn't matter. It has to have an area and it should have a closed loop. That's all that's needed. And let me represent this circular nature of this. This is making a direction associated with this. So that's your plane. So it's actually making an angle here. And that angle is, so this is your A, vector A. The direction of A is perpendicular to the loop. So if this is the loop, then that's the direction. In this case, strictly speaking, if I'm in the plane, I should just be having this. Right? So I won't see the loop at all. That's just one point. But this is a cross-sectional view. The moment I rotate it, then I see the face of that. That's your direction of the magnetic moment M. It's in the direction of the area vector, which is perpendicular to the loop. So this is the loop of wire, which from the top view is just showing up as a line. The current is going in this direction, so the area vector is this way, and the magnetic moment is exactly in that same direction. And now you ask, what is the torque on this? The torque, the simple idea is that the magnetic moment tries to align with the magnetic field. So that's the basic idea as far as physical intuition goes. M tries to align with a magnetic field. And that's what you see when you have another magnet in front of a, if you have ever played with two magnets, you will see that one magnet will try to align with the magnetic field of the other. That's because one of the magnets pretty much in principle is a dipole moment. So it's just trying to align with the magnetic field. We would like to talk about the torque. This is the torque. That's given by the magnetic moment crossed with the magnetic field. The same idea, if you want the magnitude of this, so magnitude of the torque is M times B times sine theta, where now the angle is between the M and B, right? And the direction is again right-hand rule. The first right-hand rule, whenever I say there is no second, I don't write, so it's the first right-hand rule. Again, what you want to keep in mind is that this tries to align itself with that. So it doesn't experience any force in the sense it doesn't move to the right, to the left, top, or to the bottom, but it tries to align itself. So all the forces conspire in such a way that M tries to align with the magnetic field. How you calculate this is exactly the same as what you do in the force calculation, just that this time it is M and B. That is one problem in your homework, the last problem, which asks you to calculate the torque on this magnetic moment. I'll stop here and thank you.